Hey kids, Smath here. Couple things for you in this video. This one we're going to talk about making a galvanic cell. Now this is one where we're just going to be given a couple of reduction potential reactions, and we're going to have to put them together to make a spontaneous cell, to make a cell that's going to generate a positive current. So in this case, we have these two half reactions that are given to us. We have nickel 2 plus being reduced down to nickel, and we have oxygen and hydrogen where there's an oxidation there. And so these are both written as reductions right now. The oxygen's going from 0 down to -2, the hydrogen's staying at positive. The nickel's going +2 down to the nickel 0. So what we're going to do is ding, 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 boom, reverse the more negative. Reverse the more negative reduction, excuse me, PT. Reverse the more negative reduction potential is what I meant to say in there. And so in this case, if we come back and we do this, obviously -2,3. Negative 0.23 is a lot more negative than a positive 1.23. So we're going to reverse that reaction, write it as nickel going to an oxidation, nickel 2 plus 2 electrons. That's now going to become a positive 0.23, and now leave the oxygen reaction with the 4 H pluses and the 4 electrons going to make a couple of waters. That's going to stay at positive 123. These are volts. And so our voltage here for this galvanic cell is 1.46 volts. And our concern is, hey, wait a minute. Our electrons aren't canceling. Everything we learned in balancing redox, our electrons have to cancel. But not in this case. I mentioned this earlier in one of the videos. What's going to happen is the nickel reaction that's happening out here is going to go at twice the rate of the oxygen reaction to generate those 4 electrons. We need 4 electrons getting transferred. It happens once with the bottom reaction, so the top reaction is going to have to go through 2 cycles in order to generate those 4 electrons that we're going to need. We're not going to write complete reactions with these because really it's about the rate and what I just explained, how one reaction has to go twice as fast as another reaction to generate those 4 electrons. But let's take a look at another example where we've got to write a galvanic cell. The key here is just to make sure that whatever voltage we're creating is a positive volt. So here's the second one we have where we have cerium 4 plus. And that's just taking 1 electron down and going to cerium 3 plus, and then tin 2 plus both electrons is going all the way down to tin 0. And these reduction potentials are a positive 170 and a negative 0.14. So it's pretty easy to see. We're going to reverse the bottom one. And when we reverse the bottom one, we're going to get still cerium 4 plus an electron going to cerium 3 plus. That's going to stay at a positive 170 volts. And when we flip, we're going to go tin goes to tin 2 plus 2 electrons, and that's now going to become a positive 0.14. Our overall voltage becomes 1.84 volts. So these are just standard notations of how we create a galvanic cell. You could do this if you had 2 negatives. If you had one reaction where it's going A plus an electron goes to or sorry, A plus an electron goes down to 2 plus, and you could have B plus an electron goes down to B minus, and this was a negative 0.25 volts, and this was a negative 0.15 volts. Reverse the more negative. That's all we care about here. So we would end up reversing this top one, and so we would make it a positive 25, a negative 15, and we would get a positive 10 volts. Whatever you got to do, if it says make it galvanic, make it positive. In the last video, it just said, here's your reaction, calculate the voltage. And that voltage may be negative and may be non-galvanic. It may be electrolytic. That's a battery charger where you've got to put energy in. But these galvanic cells are ones where we have to make them be positive. That's what we're doing here. Now, we have another way of designating these, and that's called line notation. It's just a real simple way, since we don't write the complete reaction for this, the net ionic for it even. So the way we write these is we're going to say anode. That anode is going to come up to a porous disk or a salt bridge, and then we're going to write the cathode. But there's two sides to this. See, this is our salt bridge. But if we recall correctly, when we were doing this in our anode side, we had a chunk of metal and it was in a solution. And so what we need to do is we're going to go anode, single line, anode solution, double line for the salt bridge, which we're going to put in right there. We're going to put a porous disc right there, to a cathode solution, single line to a cathode. The double line designates that you have a salt bridge or a separation of anode and cathode. The single line represents a change in phase or a change in state of matter. So if we take our Daniell cell was basically, it had Zn plus Cu2 plus goes to Zn2 plus Cu. And we want to write this in line notation. Then the anode is the actual physical piece of metal on that side. So our line is going to be zinc. That zinc is sitting in a solution of zinc 2 plus. Well, that's on the other side of the equation. That doesn't matter to us. We want to keep the anode side together. So this is zinc 2 plus, separated by a porous disc or a salt bridge, whichever. Then that goes to copper 2 plus solution with a metallic piece of copper sitting inside of this. It's a very simple one. There are some things that work and don't work. Let me show you a little more complicated one here. And this would be, excuse me. So now we've got copper 2 plus 2. Yep, we're going to use plutonium here, kids. Don't ask me why. It's in the example. 4 H2Os goes to copper metal plus a couple of plutonium oxides and 8 hydrogen ions sitting around. And they tell us in this example, by the way, that they need to use what's called a platinum electrode. And you'll see why when we start writing this out. So let's grab the anode and the cathode. The cathode's real easy. It's copper, 2 plus 2 electrons goes to copper, and the anode is everything else. 2 plutonium, 4 plus 4 H2Os goes to 2 plutonium oxides, 8 hydrogens, 2 electrons. Well, if we look in our anode reaction, everything's an ion. All ions are aqueous. So what do we have to do? We're going to use a piece of platinum. Why platinum? Platinum is inert. It's not very reactive. So we're going to use a piece of platinum to serve as just the site where the reaction's going to occur, where the oxidation, it's the site of that. Catalytic converters are just the site where the catalysis happens in your car's exhaust. And so we're going to write our line notation here with platinum. Now that's a solid. So now I need a single line to designate everything else, which in this case, we're going to go from plutonium 4 plus to plutonium oxide plus. So we go from the higher oxidation state to the lower oxidation state. But now we also have to include in that H plus. And we're going to include in that H2O. I'll be honest with you, it doesn't matter where you put the H2O in this, just so that it's represented on this side of the equation. Then that's going to be separated by our cathode, which is going to be our copper 2 plus phase change to our copper. That's a line notation for a pretty complex cell that has to use a platinum electrode instead of just having a piece of metal solution. All right, I'm Smath. That gives you a good snapshot at galvanic cells, writing them, calculating them, and that gives you line notation. I hope this video helped.